We just understood that charges can be spread out as bunch, as a dot, as a small unit, or it can be spread out in a continuous manner. So that continuous manner can be in one dimension or two dimension or three dimension. In this video, we're going to understand how to represent this scenario, how the SI units will be, and what kind of formulas we'll be looking at in general, right? So we need to differentiate these three cases, and we need to understand the representation that we need to have to deal with each of this. First, we're going to start off with volume charge distribution. So the basic idea here is that the charge is spread out in a three-dimensional space. That's why it's called as volume charge distribution. A term that we need to know here is volume charge density, right? We saw that dq and all of that, small charges. So whenever we talk about any material, we talk about density, is it not? So here it's to deal with charge, and we are looking at volume. So it's called as volume charge density. We define the volume charge density at any point in a volume as the charge contained per unit volume at that point. Mathematically, we're going to represent it with help of the symbol rho, and this is nothing but a small charge or a small space, right? Small charge or a small space. Now, the total electrostatic force exerted on Q naught due to the entire volume, how will it look like? Well, we know that we need to add all of the forces as per the superposition theorem. We can do that. And here we are looking at K Q naught dq by r square r cap. But as per this, what is dq? dq is nothing but rho dv. Therefore, F is equal to K Q naught integration of rho dV by r square r cap. The formula turns out to be of this manner, right? And obviously, your electrostatic force will also change. Not electrostatic force, my bad. Electrical field will also change. Here Q is 1, and it will change to this. Now, what is the SI unit of volume charge density? Can you guess? Coulomb per meter, yes, cube. Does it make sense? So that's all. We are trying to get exposed to different terminologies. Only fancy thing over here is this surface charge density, volume charge density, line charge density, so on and so forth. So here the funda is that the charge is spread across in a two-dimensional space, and we need to define surface charge density over here. It's nothing but charge spread across unit area on a surface, right? So mathematically, it's represented with, I think it's, what is this? This is sigma, yeah, sigma dq by d, yes. Does it make sense? And your total force will be K Q naught, that will come out. And here inside we have sigma ds by r square r cap, right? And r e would be K sigma ds r square r cap. And our SI unit of surface charge density will be Coulomb per meter correct square. Okay, guys. And finally, what do we have? Line charge density, the charge is spread across a line. And we define this as a line charge density at a point on a line as the charge contained per unit length at that point, right? Mathematically, this is lambda, and this will be dq by dl. Okay. And here TF being integrated. So F is equal to DF is equal to KQ naught integration of, this would be lambda R square DL small l R cap, right? And your electrical field will be K lambda R square DL R cap. And finally, the SI unit is going to be coulomb per correct meter. Right, guys? So this is all that we need to know. So here we're looking at, in this video, the different representation that we need to use in different spread, in different charge distribution. In volume, we have rho, and the formula, it's a simple substitution. Everywhere it's a simple substitution. Here it's on substituting dq as sigma ds, right? And here on substituting dq as rho dl, as simple as that. Okay, guys. You guys can pause and have a look.